Our next lesson, dealing with benzene, will talk about the characteristic reaction of benzene with its derivatives, and we'll also be talking about phenols, their nomenclature, and characteristic reactions. The far most characteristic reaction, by far most common I should say, is the aromatic substitution for the benzene ring. Groups that we can introduce directly onto the ring includes halogens, the nitro group, and sulfonic acid. And we'll take each of those one at a time and show the reaction and discuss its mechanism. Let's begin with halogenation. As we noted earlier, halogenation of an alkene occurs quite readily, no catalyst needed. We had made a note earlier in our lesson if we took a common alkene such as propene, as I drew here. We added a halogen, let's say chlorine, Cl2, could be bromine, could be iodine, but any halogen, a group 7A member. And we saw how in an alkene, very readily, the double bond broke, creating a saturated hydrocarbon, and substituting on each of those was a chlorine. So a halogenation substitution. But earlier we mentioned that benzene, because of its very stable resonance structure, did not readily react with any of the halogens. However, in the presence of a catalyst as iron 3 chloride, I'm going to write that name so you can hear the Roman numeral, iron 3 chloride, we can lower the activation energy with this catalyst. And with that lower activation energy, we can substitute on to the benzene ring. Notice that it is a mono-substitution reaction. In other words, only one of the chlorines will combine on. When I look closer, any of these benzene structure, any of these carbons have a hydrogen. So just to remind ourselves, our formula C6H6 does indeed have a hydrogen in each position of the carbon. So it is not selective where the site of attachment is. It's just one of those hydrogens is cleaved off, becoming attached to the second chlorine, and the site of attachment has produced chlorobenzene. Very similar, we could take our benzene site of attachment here with, let's say, bromine. And again, without the catalyst, no reaction. But in the presence of the catalyst, iron 3 chloride, we create a mono-substituted benzene, bromobenzene, giving us the second product, HBr, hydrogen bromide. Treatment of benzene with bromine in the presence of our catalyst, iron 3 chloride, results in the formation of bromobenzene, this compound, and the second product, hydrogen bromide. Without this catalyst, no reaction would occur. So our first of the reactions of substitutions are called halogenation. Placing a halogen onto the benzene requires the catalyst. Let's take a look at a second reaction of benzene called nitration, adding a nitrate group, NO2. When we heat benzene or one of its derivatives with a mixture of concentrated nitric and sulfuric acid, a nitro group replaces one of the hydrogens bonded to the ring. Nitric acid is a reactant. Sulfuric acid is acting as the catalyst. Just as we used the acid in the alkene reaction mechanism, sulfuric acid is required as the catalyst in the nitration benzene substitution. Let's take a look at what's happening. We have a benzene, and again, there's all the hydrogens coming off of each of the carbons, so we select one to focus on. We're adding a second reactant, concentrated nitric acid. Nitric is spelled N-I-T-R-I-C, nitric acid, in the presence of the sulfuric acid catalyst. A particular reaction would show, now let's take a closer look. I'm cleaving off this hydrogen, and I'm separating this hydrogen from the nitric acid. Those two H's will come together in the formation of water. And notice what else? The nitrate polyatomic ion, which has 3 oxygens, will only attach 2 of those, leaving that third oxygen to form the water molecule, which is our second product. HNO3, in the presence of a catalyst, will place a nitrate NO2 group onto the benzene ring. The resulting compound water is left as the second product. In a second reaction, a particular valuable reaction will reduce the nitrate NO2 group into a primary amino group. When I say reduce, it means to eliminate oxygen and change it to a hydrogen. Reduce means eliminate oxygen and convert to hydrogen. The opposite of reduction is oxidation. And just to kind of review that redox term, oxidation is the exact opposite process. Converting hydrogen into oxygen is a process called oxidation, adding on oxygen. To reduce a compound, you eliminate the oxygen, converting it back to the hydrogen. Now notice this is a very selective reaction. The nitrate group on our benzene, and notice this, that benzoic acid is our root word here. Benzoic acid, COOH, we've learned is any carboxylic acid. Our carboxyl group has a C double bond O, and the alcohol group here, OH, put that together and you get carboxylic acid. This, off of a benzene ring, we've learned to name it as benzoic acid. So here is carbon 1 in our benzene ring, and at position 4 we have a nitrate. The name of this compound, 4-nitrobenzoic acid. Knowing that it is a benzene ring with simply 2 substituents, we could call it para-nitrobenzoic acid. We want to reduce the nitro group. To reduce means to add hydrogen in the presence of a catalyst. This time we're using nickel as a surface catalyst. And 3 atmospheres of pressure is extremely high pressure, 3 times the value of normal atmospheric pressure, which is usually about 1 atm. So extremely high pressure, with a surface metal catalyst, we can add hydrogen. And if I remove 2 oxygens, you can see the formation of 2 waters, each one of those waters with 1 oxygen. 3 units of hydrogen, of course, is a total of 6 H's. 6 H's is required to hook with the 2 oxygens to make a water. So let me draw that so we can make sense. Here's our water molecules. We have HOH. 2 of the 6 hydrogens have reduced the nitrate group into amine group. 2 of the 6 have added on to the nitrogen, leaving me a remainder of 4 hydrogens, and the 2 oxygens we cleaved off of the nitrate group, resulting in the formation of 2 waters. But notice, very important, this here was not affected. Those oxygens were not reduced. So this is a very selective treatment of the nitro and not the acid functional group. When we have nitrobenzoic acid, being reduced means adding hydrogen. In the presence of nickel catalyst and very high pressure, we have reduced the we've reduced the nitro group, resulting in the amine with a remainder of a 2 water product. The benzoic acid region was not affected. So the product overall after the reduction of nitro is 4-amino-benzoic acid. The amino section resulted from the reduction of the nitro substituent group. Let's talk about a third category of reactions of benzene called sulfonation, adding a sulfate group onto a benzene. This time, notice that sulfuric acid is acting as a reactant. Every time so far, sulfuric acid has been a catalyst. We've seen it up on top of the arrow. But this now becomes the substituent group we'd like to place on the benzene ring. Therefore, it is shown as a reactant. Any of these 6 hydrogens off of the benzene will get cleaved. We need a site of attachment, so keep in mind the acid hydrogen from sulfuric acid. One of those is cleaved off, and just kind of showing that structure, we would have a Lewis dot structure of sulfuric acid will look similar to this. Sulfur is the center atom, 4 O's in each direction, and the protonizing hydrogens right here. So we're going to cleave one of those hydrogens to create the site of attachment. Alrighty. Now we'll write that as SO3, 1 hydrogen remaining, as a byproduct of water as well. By removing one of the hydrogens and by removing one of the oxygens with a hydrogen, I'm going to make this better. I'm going to draw this, and I'm sorry, you're going to have to erase probably with me. I accidentally drew the cleaving here. It is not. It is here. So if you need to make that repair, that's a very important repair to make. That this particular cleaving, breaking of the bond, occurs here. I accidentally, a moment ago, drew it in the wrong location. Because now I can see cleaving one of these hydrogens. Let me change color to make that more emphasized. Cleaving this hydrogen from the benzene and cleaving this OH group from the sulfuric acid structure, H2SO4, now you see the point of attachment directly on the sulfur. And that's how we have it written now. We break off an OH group from sulfuric acid. We create the site of attachment as one of the hydrogens. You can now see where the water is the byproduct, and we have SO3H, benzene sulfonic acid. Benzene sulfonic acid is a very strong acid, even comparable in strength to sulfuric acid. So keep in mind this now would have the site of attachment. You'd have your benzene ring. You'd have it attached to an S, O, O, and still have the acid proton at the end, giving us the second byproduct here of water, HOH. One of the major uses of sulfonation is the preparation of synthetic detergents, and an important example of which is the following. Dodecylbenzene, and this is probably a prefix we might not have heard. It literally means 12 carbons. We were only asked to memorize the prefixes up 1 through 10. Methyl, ethyl, propyl, butyl, pentyl, hexyl, hepta, octa, nona, decyl. Well, we could keep counting. If we kept counting to carbon 12, dodecyl is what we would hear. Carbon 1, a chain of 10 carbons in a row, and another carbon. 1 plus 10 plus 1 gives us the 12 carbons attached to a benzene ring. With the treatment of sulfuric acid, step 1, we would create, as we know, a structure as above where we would place on a sulfonic acid group onto the benzene ring. You can see that site of attachment would be directly opposite the corner here. So our intermediate, if you will, would have the HSO3 functional group coming off of the carbon. In the second treatment, NaOH is then used to neutralize the acid. Let me draw this intermediate for us so we can see. Step 1, and this is that long carbon chain, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we had 12, 11, 12. So there's that long carbon chain. Kind of see that long tail, dodecylbenzene. The opposite side, step 1 of this two-step process, that's a single bond, created the structure as above. Benzene sulfonic acid except now we have a tail on the opposite end. Dodecyl benzene sulfonic acid. Step 2, we added NaOH. Remember, this is a strong base. This is a strong acid intermediate. When we treat an acid and a base, they neutralize each other. They make a salt and a water. I need an arrow. We know it makes a salt and water. Acid plus base makes a salt and water through a process called neutralization. Well, if I treat this with NaOH, let me change color. I add on NaOH in a second reaction, NaOH step 2. We can see really as a double displacement reaction. This hydrogen, this hydroxide group come together to make a water. And the salt that is produced places the positive sodium ion onto the acid functional group, sulfonate. So we get this salt, and the other product, even though it's not shown, the process of neutralization would also make a water molecule. This H and this OH come together to make a water, leaving the positive ion of sodium and the negative ion sulfate hooking together to create this salt. Sodium 4-dodecyl benzene sulfonate, commonly called SDS. These detergents were introduced in the late 1950s as a replacement to the natural soaps that were then being marketed. Natural soaps were made with base sodium hydroxide, commonly called lye, L-Y-E. However, now, because of these synthetic soaps being so easy to produce, very economical, much easier to produce than by saponification of those bases, they now have over 90% of the market that were once held by the natural soaps. So just an interesting reaction of acid-base chemistry creating a salt that now has over 90% of the market of detergents. Let's now talk about phenols, the structure and nomenclature. These functional groups of a phenol is a hydroxyl group bonded to a benzene. We introduced this much earlier in the last lesson and said, you've introduced yourself, now memorize its name, phenol. Just as they had many common names of benzene by the attached functional group, those common names are indeed the IUPAC names. The same is true when we name these phenols. There are many common names that we just need to know. The first, of course, phenol with the functional group of an alcohol, OH, as a substituent group on a benzene. If we have a methyl group, CH3, methyl group, 3-methylphenol, 1, 2, 3, carbon 3. You might hear meta-methylphenol, but most often we're going to hear it called cresol, meta-cresol. Now, when we have a benzene that has a OH, we know it's a phenol. And when we had a methyl group, CH3, we learned, again, this is back in section 2 when we were trying to learn the names. If we had a methyl group, let me just draw a second structure here. Just a simple methyl, we called it toluene. And if I had, not the CH3 group, but just the functional group phenol. But now we have them together. If it's strictly a CH3, we called it toluene. If it's strictly an OH, it's phenol. What if they're both together? Now the word becomes cresol. Metacresol, here is orthocresol, and OH position 1, CH3 position 4 would be paracresol. 1-methylphenol, 4-methylphenol, 3-methylphenol, but we're getting the idea that we commonly hear these names in IUPAC, cresol. What if we have two functional groups in which both are OH? Here this diol to represent two functional groups of an alcohol, OH, diol. 1,2-diol would be would be orthobenzene diol. Here is meta, 1,3-benzene diol. 1,4 would be para, 1,4-benzene diol. However, get familiar with these names: catechol, resorcinol, hydroquinone. Two functional groups just based on the position of both OHs, and you hear three different common names. Orthometa-para position, turn it from catechol, resorcinol, and hydroquinone. Phenols generally are weak acids with pKa values approximately 10. The larger the number, the weaker the acid, and this is a very large number. So phenols are indeed weak acids. P just means negative log, so the pKa value is 10. There are other Ka values that we studied in acids and bases, but in an earlier course. The larger the value, the weaker the acid. Most phenols are indeed insoluble in water, but they react with strong bases such as NaOH or KOH, potassium hydroxide or sodium hydroxide. And when they do so, they form water-soluble salts. Phenol, who has a pKa 9.95, which means it's slightly stronger than pKa of 10, but not by much. Only slightly soluble in water, which is unusual because we might think of this as a polar molecule, and water is polar, so why aren't these two dissolving? The answer lies in the benzene ring. The benzene is such a non-polar dominating structure to this molecule that the dispersion forces do not allow it to actually interact with the hydrogen bonding of water. So here, the dispersion force of the nonpolar region has far more intermolecular attractions than the polar region of the molecule. Even though this exhibits hydrogen bonding, the dispersion force dominates. When we react with sodium hydroxide, keep in mind sodium's a plus, polyatomic base ion NaOH, sodium hydroxide. We can see the point of cleaving right here. The hydrogen is taken off of the phenol, leaving this a region slightly negative. The proton here, the hydrogen, now attaches to the hydroxide, resulting in a water molecule. And the salt that is produced, again, sodium positive, and the oxygen is left negative after cleaving off the hydrogen, creates this salt, sodium phenoxide. I'll say it again, sodium phenoxide. A much weaker base, and now is very soluble in water. The positive ion of sodium can very nicely dissolve in the water. Phenol, which is insoluble, turns into a water-soluble salt with treatment of a strong base, such as sodium or potassium hydroxides. Because these phenol groups are quite weak acids, they do not react well with weak bases, such as sodium hydrogen carbonate, NaHCO3, we call that baking soda, or ammonia, NH3. No reaction for weak bases. They only react well with a very strong base, which has the ability to pull off this proton, breaking that OH bond from the phenol. Weak bases are not capable of doing that. Some phenols we find in nature act as very powerful antioxidants. Take a look here. We have isopropyl, see that isopropyl group, that 3-carbon branch chain, coming off of a phenol group of the benzene. And the opposite corner here, I see it carbon 1, 2, 3, oops, this is carbon 1. Let me renumber. 1, 2, 3, 4, 5. We have a methyl. So we have 2 isopropyl. At carbon 5, we have the methyl phenol. IUPAC name would name both substituents group from the base word phenol, 2-isopropyl 5-methyl phenol. But most people will say, in the world of chemistry, thymol, a common name from the IUPAC name. Notice this functional group is a benzaldehyde. So I see my root word here from carbon 1 as benzaldehyde. Here I have an OH functional group, hydroxy, and here we have a methoxy. Hear that? Meth from one carbon attached to an oxygen, methoxy functional group. It's the major component of vanilla, 4-hydroxy, 3-methoxy benzaldehyde. We hear it called vanilla. Here we have 2 functional OH groups on a phenol, and we have a long carbon chain coming off here. There's a total of 1, 12, 13 carbon chains. This is the major component in poison ivy that gives us that irritating rash. Urushiol is how you would pronounce the component in poison ivy. And this was the opening picture in your chapter that talked about peppers being an antioxidant. And this is a structure there of what the major component is of peppers, hot peppers, chili peppers. The reactions called antioxidants, they're going to go through and show this step-by-step process known as chain propagation, a very common organic reaction that produces just thousands and thousands of long monomers turning into a polymer. The process called auto-oxidation. Now what I just said, put 2 O's in there. Auto-oxidation. But in order to eliminate the double vowel, we'll call it aut-oxidation. It's a reaction that converts an RH group to an ROOH group, known as a hydroperoxide. You know, sitting in your medicine cabinet at home, most likely you have a compound called hydrogen peroxide. Looks like this. Now you get a cut, you put a lot of hydrogen peroxide, starts bubbling out and killing bacteria. H2O2 is called hydrogen peroxide. When it's attached to a carbon chain, it is called a hydroperoxide. Let's take a look at the overall reaction first, and then we'll break it down into a step-by-step reaction mechanism. Overall reaction shows a section of a fatty acid hydrocarbon chain. Now, at this particular point, we may or may not have background knowledge on fatty acids, but they're extremely long carbon chains that are not saturated. So in other words, right here is a double bond, giving me an alkene. I don't know how many carbons there are, I just know that's an extremely long chain. The process of auto-oxidation is adding oxygen, see the O2 reactant, in the presence of heat or light to initiate the first of the 3 steps that we'll look at. In the presence of oxygen, O2, and heat and light, remember this is overall, we have to break this down step by step, the carbon not involved in the double bond, but the one immediately after it, is now going to add on the OOH, the peroxide functional group. Hydroperoxides have been made. Notice here I had alkene in this part of the structure, and the site of attachment of the OOH is the carbon next to the double bond. It certainly could have been this carbon as well. If I just spun the molecule in a 3-dimensional way, we would be looking at that carbon instead. So either one would undergo this auto-oxidation process. Not the carbons involved in the double bond, but the one immediately next to it. Let's look at this process known as a radical chain reaction. In step 1, we have to initiate the chain. It is called the chain initiation, where we form a radical from a non-radical compound. Let's review radical. I know we covered it in inorganic. A radical is an atom or a molecule with an unpaired electron. Because it has an unpaired electron, it is left with an exposed negative area. Just a little side note, we know that carbon needs to have 4 structural bonds to create the octet, which is 8 electrons. These structural lines we know to represent a single bond. If I break the bond between the carbon and the hydrogen, for that moment in time, let me erase that and draw that better. And it is just a quick moment in time. We have an unpaired electron on the carbon as well as an unpaired electron on the hydrogen. Those will become the sites of attachment when they go on to form the product. They hook to a new element. Well, this right here, this carbon here has 7 electrons total because there's this one unshared electron here. This guy is unpartnered. This indeed makes it a radical. Hydrogen, instead of the 2 it would like to have to become it doesn't get an octet, it only needs 2 to become like helium. But this unpaired electron creates a radical of hydrogen. A radical is any molecule that's broken a bond, and the site there where it was broken has an unpaired electron. That is the position in which a new bond will form. So step 1 of oxidation is creating a radical, a site of attachment. To initiate a chain, and again this is a step-by-step process that occurs over and over and over again, creating very long chained molecules, we first have to create from a section of a fatty acid a site of attachment, known as a radical. The initiation is done by light or heat. The carbon immediately following the double bonded carbons from the alkene section of the fatty acid cleaves off the hydrogen. Notice here in our slide that unpaired electron is denoted as a red dot. This is the radical that's produced. We also now have a radical out there. It's not shown, but there's a radical of hydrogen out there from cleaving off this site. Step 1, when we initiate the chain reaction, it's called chain initiation, we form a radical from a non-radical compound. The non-radical compound is a long section of a fatty acid. In step 2, we begin the chain propagation. This is when a reaction of the radical changes to form a new radical. We'll call this step 2A, and we'll talk about a further step called step 2B, and we just see this propagate over and over again. Here is the product of step 1 now becoming the reactant in step 2. Right here, not shown well, let me make that darker, is the radical region of our fatty acid chain, the carbon immediately following the carbon that's involved in the double bond. Recall from the overall reaction through the process of oxidation, we're trying to add oxygens. Now, oxygen molecular oxygen, we know it to be a double bonded O2. This is not that at all, is it? It's known as a di-radical. Notice that it only has a single bond at this position, and here's a radical site at each end of the molecular oxygen. So in nature, as I'm breathing in air as O2, O is double bonded to itself, creating an octet. But that's not the reactant we're showing here. Oxygen as a di-radical has an unpaired electron on either side of the oxygen molecule. Those will become the site of attachment. So notice here the site of attachment on our alkene group and the site of attachment on the oxygen. That will be, in our first step I'll call 2A, the site of attachment to create a hydroperoxy radical. Chain propagation says I'm going to take a radical, in which we had here from the hydrocarbon chain, and create a new radical, which now we have up here on the oxygen on our hydroperoxy group. Step 2A, take the oxygen and add it onto the carbon next to the double bond. This reaction produced a new radical. Step 2b, I'll call this step here, 2b, propagation of step 2. So chain propagation, in which we take a radical and form a new radical. Now that's getting familiar, isn't it? Here's a radical that we just produced up above in step 2a. Notice now the oxygen has the unpaired electron, giving it its radical status. And here's that new section of fatty acid hydrocarbon. This was like the initial starting material from step 1. Notice the carbon next to the carbon in the double bond becomes the next radical we form. Here, we cleave off this hydrogen, and that's the hydrogen that ends up to create this peroxide group on the hydrocarbon chain, leaving this particular site as the next radical to begin up here in step 2a. Step 2a starts with a radical of the hydrocarbon chain. Step 2b produces the new radical, and I can see this chain process going on and on and on to create thousands and thousands of hydroperoxide molecules. That number of times the cycle perpetuates or propagates, repeating over and over and over, will determine what is called its chain length. Thousands and thousands chain length long of carbon. Hydroperoxides themselves are very unstable, and under biological conditions they degrade to short-chain aldehydes and sometimes even carboxylic acids. They have a very characteristic unpleasant odor. If something, quote, has spoiled or become rancid, it is because of this very reaction. A hydroperoxide propagation has occurred, creating this rancid smell. Sometimes a tub of butter will become rancid as those fatty alkanes undergo peroxide propagation. Similar formation of hydroperoxides in the low-density lipoproteins, we call that LD, low-density lipoproteins deposited on the walls of our arteries, leads to cardiovascular disease. And the last point it makes, in addition, many effects of aging are thought to be the result of hydroperoxide formation and their subsequent degradation. We look for natural molecules that help with this process called antioxidants. Antioxidants. We want to prevent this very reaction from happening. If we can prevent this propagation with an antioxidant, we can prevent the formation of plaque in our artery walls and so forth. One of the most common antioxidant is vitamin E. Take a look at its structure. Here's a second example called butylated hydroxytoluene, BHTs. And butylated hydroxyanisole are known as BHAs. As I mentioned, vitamin E might be the most common one we hear of in our diet. The reason that these act as synthetic antioxidants, as in BHT or BHA, vitamin E we know occurs in nature and in our normal diet. It is a natural antioxidant. These are radical scavengers. They will propagate instead of the peroxide, forming much more stable radicals and break the cycle of that propagation. So in other words, they're working to prevent the propagation of these hydroperoxides that form. Unfortunately, vitamin E is removed in the processing of many foods and food products. And to make up for their loss, phenols such as BHT and BHA, as we're looking at their structures here on the slide, they're usually put into food as food additives to help retard spoilage. So again, we're looking at a way of processing food to prevent it from spoiling, but in also kind of taking out the natural vitamin E's that occur through the process of cooking. This ends the chapter on benzene and its derivatives.